everybody, do you hear me?
Yes.
I will share the link in the chat for the test. I mean, it's our every lesson we have refresh test, so it is it. Well, when you will finish it, please let me know, and we'll discuss all the questions. We'll go through. And I hope we will have today a little bit shorter lesson because it's extra lesson about attention. Just refresh all our knowledges, and also we will have a look through different techniques of attention. So I hope we will finish it earlier. Hi guys, yeah, we have test right now. This short overview of questions to refresh our knowledges. So I think everybody who joined the conference, they didn't see the link. I will duplicate it and So you can go through the link and also have a look through the questions, and then we will discuss all the answers. I think 4 minutes would be okay for finishing the text. The test. And then we will start. Okay, guys, have you finished yet? Anybody?
Yes, I finished.
Yep.
Yeah, okay, all right. So I will share the screen and then we will discuss all the questions. So here, what do we have? The first question was about attention mechanism in sequence-to-sequence models. So let's go through all the options and discuss is it correct or incorrect. So the first one decreases the computational complexity of the networks. It is incorrect. The attention mechanism adds operations, so it increases the complexity. The second one was increases the computational complexity of the network. It is correct option. Attention introduces additional matrix multiplications and operations, which increase the network's computational load. And the last one was about doesn't affect the computational complexity of the network. It's incorrect because, as mentioned, attention mechanisms require extra computations, so they do affect the complexity. Any questions about this question?
No.
Okay, so let's move on. The second question was attention lore in RNN encoder-decoder architecture is applied. And we need to choose one option. So the first one is incorrect because the attention mechanism is used after the encoder processes the input and while the decoder is generating the output. Second one was about decoder. It's incorrect too. Attention mechanism is not applied after the entire decoding process. It is applied at every step of the decoding phase. And the last one is correct. The attention mechanism is applied during the decoding phase, helping the decoder to focus on relevant parts of the encoder's output sequence for each step. Okay, here the next question was about self-attention. Self-attention scores computed for selected input, query key, and value vectors are generated. The scores for the selected input are computed. And correct answer was 1, 2, 3, was this one. Because for self-attention, the query vector is compared with each key vector to compute the attention scores. Is it clear?
Yeah.
Okay. So on the next question, we need to choose a right option, select one. So here, the correct one was without normalizing scores, alone hypothesis would get lower scores than the short ones. It's correct because beam search tends to favor shorter sequences. If scores aren't normalized, as longer sequences accumulated, more probability loses. Do we need to discuss why this one is incorrect?
No.
Okay, all right. So here, correct answers is second one and the last one. Let's discuss why the first one is incorrect, because while it was originally designed for sequences, self-attention can be adapted to other data types, such as images or graphs. Second option is correct because self-attention mechanisms are efficiently used in vision transformers for image processing. And So I think it's clear that it is just right, and that's it. So okay. Any questions in this moment? If not, we will discuss the last question. And here the correct answer would be the last one, because without positional encoding, self-attention loses the ability to consider the order of the sequence, making the output insensitive to input shuffling. And the first one is incorrect because without positional encoding can be applied to any data type, not just text. And the second one would be incorrect because without positional encoding, the attention mechanism has no way of distributing between different positions in the input. By the way, was in the lecture recorded files, yeah, that what was recorded this lecture. Did you have positional encoding, or it's not familiar to you?
I think we had it, but if you don't mind, can you summarize the main
Yeah.
point?
Okay, I got it. So maybe if you, I don't know. I think it would be in the next lecture in Transformers. I didn't recognize that maybe you didn't have this. Okay, I will refresh all the information, but maybe today we will go through another notebook with code. It's short, and we'll just view what is positional encoding on the practice. So okay, if we will start with summarizing information about it, it's just okay. Let's start from visualization. It's our today practice, but we will start from just empty space. So okay, when you pass the sequence, let's imagine that this is our sequence of text, for example, but we don't mind what type of sequence we have. Maybe we can pass sound there, or biological terms. I mean sequence of like okay, you need to know from what proteins consists. So yeah, let's imagine that this is sequence, and we need to understand how far this step from that one, for example. We need to understand it because in the text, for example, we have semantical distributions, and if we would know and if we would know how far away this token from another, we will understand grammatical rules of our language. In this case, we need positional encoding. So it's just in a regular positional encoding, we have sinus and cosinus formula. It's look like it's look like this. Okay, look at this this picture. Here we have positional encoding after embedding layer. When we mapped our tokens to the vectors, and we need to concatenate positional information. And here we can see how does it look like. Here we see just a visualization of positions of our sequence. And here we have depth. We can recognize here that color just show us how far away one part of sequence from another. And this type of information help us to understand some grammatical rules of our language and other. So I need to check, did you had, okay, I will stop my screen sharing for a while. I want to understand, you have in the course notebook of positional encoding. Yeah, you have. So I will just open it and maybe we will discuss it today, because it is short. We will open it here. So did you get the information? Did you get what did I mean?
Yes. I just wonder why we cannot just use the just the number of the word in the sequence, instead of using kind of complex formula with periodic functions like sinus and cosinus. So why not just a simple number? Is it the word number or token number 0, 1, 2, 3, etc.?
Okay, yeah, I got the question. Maybe I will reformulate it. Transformers, unlike RNNs, do not capture the order of input tokens. So in RNN, the sequence is processed one token at a time, which naturally encodes the order of the data. And in transformers, all tokens are processed in parallel. So this parallel processing means that transformers have no built-in understanding of the position of our order of tokens in the sequence. And to overcome this, positional encoding is introduced. It's provide the model with information about the relative of absolute positions of tokens in a sequence. And they allow the transformer to account for the order when generated output. Did you understand in this case?
Yes, it's a nice explanation. Thank you.
Okay. So yes. Let's move to attention mechanism. 1 second. I don't see my screen, full screen. Okay. So here we have more, okay, we have extra information about attention. We discussed on previous lesson attention operations, this mechanism. So in this seminar, we will cover how attention mechanism work. We will explore some more types of attention, and we will include implementing and visualizing the attention mechanism, as well as training sequence to sequence again model. So let's go through and let's start from the first part. So here to begin, let's visualize some hidden states to understand what is happening inside the model. I will just run code blocks. So a hidden state in RNN holds information from previous time steps in the sequence. It allows the model to remember information and use it to generate output. Here we visualize a decoder hidden state as a heat map, which help us understand the model's internal representation of the sequence to a given point. And here we can plot, okay, in a sequence-to-sequence model, the encoder process the input sequence and generates annotations, I mean hidden states, which the decoder attends to when generating output sequences. Here we visualize a single annotation from the encoder. Now let's implement the attention mechanism. First, we will use a dot product attention mechanism where the attention score is calculated as the dot product of the decoder hidden state and the encoder attentions. Let's create code for this method. Here we need to implement dot product of the matrices. We need to pass their hidden state of decoder and also encoder hidden state. In this case, it would be work. Okay, so we can see the value and the dot product is a simple way to measure similarity between two vectors. In attention, the dot product tells us how much focus the decoder should place on practical encoder hidden states, and we name it attentions. So next, we move to calculating attention for multiply attentions. Here we have these two parts of code. So this represents multiply attention produced by the encoder at different time steps. Each column corresponds to a hidden state for a practical input token. Now we will calculate the attention score for each annotation using the dot product. We can see here some formulas, and we will implement this method. So we need implement dot product, but here we would pass again we will pass decoder states and annotations. And now we can see the result. So we just multiplied few matrices. So after obtaining raw attention scores, we apply a softmax function to convert the scores into probabilities, which will then use to write the annotations. And here we have code for this operation. Softmax normalize. Okay, I will ask you. Do you understand what is going on here? Why do we need what softmax do? And maybe you just can summarize all the code that we have here and explain how does it work. If it is tough to you, I can do it by myself, but it would be nice practice for you to just discuss the code, and in the future it would be more convenient for you to understand maybe work code repositories for with similar functions. Okay.
So basically, can we go like to the top? So maybe like can discuss it to the code, because you wanted us to understand what's happening.
Can you what do you want to say that I should explain what is going on here, right?
No, you wanted to for us to explain what is happening,
Yeah.
but we only at the end of the what's happening, right? So basically, before we computed the row attention scores that was done before, and what's at the top is we're basically applying softmax to normalize the scores.
Yeah. How does it normalize? Do you understand here?
Yeah, I mean it shows from the formulas. So we want attention weights to be to sum up to 1, right?
Yeah. It's perfect discussion of the code. Yeah, it's true. So our probabilities sum up to 1, and this ensures the model focuses more on relevant part of input sequence. Great.
Yeah.
Okay, let's move to another function. Here we apply the attention scores to the annotations. Here we need do this operation. Just need multiply our matrices. Oh, sorry. Yeah. Wrong. Ah, okay. No, it's true. Much. A little bit strange. We passed attention weights here. Let's just print it. And patience. Okay, it's another dimensions. So let's where we got notations. It's strange a little bit, maybe without. Okay. Okay, so here we need weighted attentions represent the model's contextual understanding of the input sequence, and each annotation should contribute the final output based on its current base on its attention bytes. So I can't understand what is wrong here. No, I see that we have different dimensions here, but in formulas it's all right. Okay, maybe I will stop the screen share. I will search for this error, and maybe we will could understand what is wrong. Give me 5 seconds. Okay, maybe we can fix in this way. Let's just do it like this. So, okay, next we can print a heat map of this one. And okay, we discussed that weighted annotation represents the model's contextual understanding of the input there. And here we need to calculate attention context vector. Here we have done code for this one, and we can plot it. Here we can see the attention vector is a context vector that summarizes the input sequence, focusing on the most relevant part. based on the attention scores, and we can see heat map for all that operations. So let's implement general attention mechanism here. We introduce a more complex attention mechanism, general, which involves learning a transformation matrix to map the annotations into a new space before computing attention. Here we need just print something like randomized, random something like this one, and general score would be dot product of that dot product we will pass order, and our matrix, and then here I will pass annotations. General attention learns transformation of the attentions, allowing the model to better capture complex representations between the encoder and decoder. And then we can implement concatenation-based attention type, where the decoder, hidden state, and encoder attentions are concatenated and transformed before computing attention. So here we need just initialize our matrices with random matrices, like in this dimensions, and the vector with these dimensions. So here we will have okay, we just can start with concatenation. And then we need to initialize ASICs of our transformations. So then we need create dot product of this value that we concatenate and our matrix. And then we need to get a flatten vector. And then summarize it with our vector. So do you understand what is going on? Why do we flatten, for example, our matrix and then summarize it?
No, somewhere I got lost.
Okay, yeah, I will explain you, and then I will check what is going on. Yeah, because we need to summarize with another vector. So here we have a matrix with dot product. Then we need to flatten it because we need to have one vector from matrix, and then we can summarize it. In this case, so okay, 6-1 is out of bands array. Okay, let's check what would be on this operation. Here. Okay, so we have array. So let's print the shape. Both sides. Okay, so we have transponation of our tensions and 6. And here we had stations. Maybe something like this would help us. Oh my God. Okay, so maybe let's just do it in another way. So here we can pass annotations. Here it would be okay. And then we can combine, concatenate, and it would be work maybe if I would do this one. And here would be other hidden state and notations, but I would put shape. Okay, so let's check. Concatenate tile. Okay, yeah, of course. And tile.
You have extra one. It appears this extra one is not expected here inside the tile.
Yeah. Oh, 1 second. Okay. I see it. I see it. Okay, if I would do something like this. Okay, so please, I will rewrite just. Okay, so concatenate this will have A61. There we will put tile. Okay, I would put array with tile. And then I will pass hidden state. And here would be patience, shape, and now should it work? Yes, okay. And then we should this combinate function, we should pass to dot product. Okay, that would be scores. We will have dot product. Function and our metrics. And then we would summarize this vector. And we will then return scores, but in flatten view. Okay, so here we get annotations, shape, dimension, and length of decoder state. We can see how does it look like. And we can see now how combinate value looks like. Yeah, and there are different sizes. So let's just put here something like this. And then okay, which dimension should we pass here? Did everybody solve this? Okay, let's try in another way. Okay. Then would be, let's just transpose annotations first. Then we will have hidden state repeated with style. Yeah, but I think we would have the same problem right now if we would. Let's try. Oh. So maybe work here. And then flatten. Okay, so we did it. Okay, here we have white matrix has okay. Did you understand what did I do? So we had dimension mismatch because the concatenation between hidden state and annotations required that okay, their shapes, and we just we generate matrix in these dimensions, and this ensures that the concatenated vector and the weighted matrix align for multiplications. Then we used tile. This operation creates matrix which row is the decoder hidden state, which can then be concatenate with annotations. And then we concatenated in the result of the dot product, we flatten the vector in the one-dimensional array of attention scores for simplicity. So, okay. Let's move a little bit further. So before training sequence-to-sequence model in this notebook, we need to process the names dataset. This involves tokenizing the names into characters. Let's just run all the codes of club here. And I will show you a function about that I talk. Okay, yeah, so here we have functions. In this function, we map characters in names to the corresponding integer IDs and pad shorter names so they all have the same length. This format is required by RNNs. Let's run it. And so here we have a model, and we can run all the code blocks that we have. Here, all the code would work, I think, but I won't move to sequence-to-sequence model because it would be a more interesting part. Here, we can define our sequence-to-sequence model as on previous, we had 2 previous lessons where we discussed this architecture. So we know how to implement encoder part and decoder part. Let's just run it. So do you remember how to implement encoder decoder part? And here we need initialize encoder first via class and decoder. And here in the forward, we should first pass input to encoder part. So let's name it output of encoder. Output. And also it would, as you can see, it would return hidden states. We should initialize hidden state of last layer 2. And then we would pass in this class our input data. Then we should return the decoder. Hidden states of encoder we pass to decoder layer, and then we'll return decoder output. And here, okay, I will just repeat. Encoder encodes the input sequence in a hidden state, and decoder part generates the output sequence using the hidden state provided by encoder. In this implementation, decoder is feed the ground truth sequence in which consists from target value during training. And this method calls teacher forcing, where model learns to generate the next token based on correct previous token. And we discussed it on previous lesson. So we can run this code, and we use the matrix function, matrix here. We defined it earlier. We use it to prepare batches of data for training, and we can convert both the input and target into matrix format. We are randomly selecting a batch of 32 names from the dataset and converting both English and Russian names into matrices of token IDs. These matrices are used as input tensor and target tensor for the model. And here we need, yeah. Okay, I thought that somebody turned on a microphone and wanted to say something. Okay, here we should write the code that would train our model. We had initialization of our model, so we had optimizer, we had criterion, what we would use. Here we have negative log likelihood loss for classification tasks. Let's try to implement training loop. Let it be 100 epochs. So the first one we will. Okay, we have defined in the model and prepared data, we can train our model now. And in the training loop involves spacing input sequences through the model, computing the loss, and update the model parameters using backpropagation. So I will write the code, and then I will discuss what is going on in each step. Okay, so Receivers better. Okay, let's I just explain you what is going on. It's kind of weird errors. I will check what is M letter here. So the input sequence is passed through the encoder, and decoder generates the target sequence. We use negative log likelihood loss, which is suitable for classification task, like predicting the next token in a sequence. The optimizer is ADAM, a common choice for training neural networks. And the losses provided every okay, we didn't type where would be a loss provided, just print it. And here we have get examples in the last case. So here, this is function converts the token IDs back into characters using the IDs to token mappings. We can display the original English name and its translated Russian equivalent for a specific index in the batch. And also we can monitor the training process more efficiently. We can use TensorBoard to visualize the loss during training. I would, okay, I did, by the way, I did the branch for our course. And I don't know what's going on. Yeah, okay, so yeah, and here I would attach this file with TensorBoard, because we have only 10 minutes left for the lesson. So I will explain you what is TensorBoard and where can we see it. Here I ran the code, and there was a summary writer from Torch library, and you can visualize your training loop or evaluation, and you can see a graphic of your loss. So TensorBoard provides a graphical interface to track various metrics, such as accuracy or another one, and loss too. We log the training loss at each step, and after running this code, you can start TensorBoard and visualize the training process in these operations. So and you will see all the process what you want. Also, you can use another techniques to mention your metrics. For example, you can use 1 second. It names okay, we can use ClearMail, we can use TensorBoard, we can use No. I forget the name of this specific technique. So if you want, I will provide you, but it's more convenient than TensorBoard, and I like it more, but I forgot the name of this. So let's just summarize what we covered today. We discussed attention mechanism. We implement dot product attention, general attention, and concatenation-based attention. And also I provided you material of JLMR, and you could read about self-attention mechanism. Okay, it's not this blog post, but it's similar to this. Yeah, and in transformers we use self-attention. So I think maybe after this code blocks with this implementation and that one, maybe it would be more easy to you to understand, easier to you to understand self-attention and attention in transformer, but I think we would discuss it on next lesson. Maybe you have a question for this lesson for this moment.
So did we actually implement self-attention in this notebook?
No, in this not, but
Okay, yeah. Oh, I just thought maybe I missed it. Yeah, because I understand we didn't, but like just wanted to make sure.
yeah.
Also, are we gonna have new homework?
No, you had girls they needed to send you second homework, and you have it, and you will have a deadline on give me a second.
I think we only had one homework.
No, they should send it to you the second one. I will ask them did they, but yeah, we discussed with them that they would okay. I think 1 week ago Valeria needed send you second homework.
Valeria. I only know Елизавета.
Okay, I will discuss with them. Maybe Beta will send.
Yeah, we definitely didn't receive any homework. That's why I was asking, because you said it's gonna be 5 homeworks, and I was like, okay, that's already been like weeks since you. Yeah, so basically we definitely didn't receive any homework.
Okay,
Absolutely. We had no homework at all, and I have no idea who Valeria in fact is. So it seems to be a misunderstanding, and my course mates, they do not know anything about homework as well, so we didn't even start it yet. So please send if there is one. And in fact, if the deadline was about to be, well, quite soon, we will probably ask you to delay it, because we haven't even seen it yet.
I will duplicate a link for Google form in the chat. Please.
Okay, thank you. Thanks a lot.
I sent it.
Okay, thank you.
Yeah, so their deadline was 25th of October, but I think it would be okay if you will pass it on 1st of November. It's okay for me because on the next week we will have transformer lesson, and then it would be a beard lesson. And after, okay, maybe not, I will check which date would be okay for finish second homework.
Okay, thank you.
Okay, thank you.
Okay, so we can finish our seminar. If you haven't got a questions. So have a good evening. Thank you for
Thank you. Will you be sending the notebook with the correct code?
Yeah,
You're just gonna put it in repository, right?
Yeah, I would put it in the branch of this year. I will send in the Telegram chat branch of this year too, and I will put it there.
Okay. Thank you so much. Have a good night.